Welcome back to the ninth chapter in multi-body dynamics using Altair HyperWorks MotionView MotionSoft. In the previous chapters, you built up a working model of the 4-bar mechanism. So in this chapter, you'll learn about the CAD import utility within MotionView environment. And you'll be finishing up with the first module, wherein you'll be able to simulate the automotive trunklet mechanism. Let's talk about the MotionView CAD import utility. So MotionView CAD interface relies on the Hypermesh CAD import engine. MotionView has a CAD import tool which supports importing from different types of CAD tools and FE formats. So MotionView has the following capabilities that can be used on the CAD geometry. So they include importing of each component in the full geometry as an individual separate part with mass, center of gravity, and inertia calculated automatically. Moving on to the second point, we also have the option to import the geometry alone without its associated mass and inertia properties. In this case, no part is created. The major advantage of using this tool is that the part or the geometry gets meshed automatically. The surfaces of the components are meshed and exported to a specified graphic file format called the H3D file format for visualization in MotionView. Each component collector is brought into MotionView as a body, and the mass and inertia properties are determined on a unit density basis, provided Hypermesh is able to create solid entity successfully. You then have the option to specify the density for each body based on which the actual mass and the inertia are assigned to the body. So the import tool also has a feature to launch Hypermesh, and you'll be able to work interactively to mesh the surfaces as chosen and select the nodes that can be imported as points. We also have the option to position the geometry in the MotionView model. Now let's discuss about the various CAD or the FE formats that are supported in MotionView model. So MotionView supports the following CAD or the FE formats. So you can import files from CATIA, Hypermesh, OptiStruct, Parasolid. So it can be a Parasolid file, or from ProE, you can import a step file, JT file, any file from SolidWorks, and UG. So now let me invoke the CAD import utility by going to the graphical user interface of MotionView and show the various options available in this particular dialog box. And switching back to the graphical user interface of MotionView. So there are two ways of importing the CAD import utility. So there are two ways of invoking the CAD import utility. First thing is to go to this file option that you can find and then go to import, and from there you can go to geometry. So this brings up the CAD import utility dialog box. This is one way of doing it, and the other way is by simply clicking on this particular icon which says import geometry on the toolbar. So if you click that option, you can come to the same dialog box that you got earlier. Okay, so this is just a shortcut. So here it's divided into several sections. For example, the import option section, input output file name section, the MDL section, the meshing options for surface data section, and the locator point section. So these are the various sections in this particular dialog box. So let's see what all these options refer to. So under the import options, you have two radio buttons. So the first radio button, as the name suggests, is to import the CAD or the FE model along with its associated mass and inertia properties. So say you've built a model or you have a model in CATIA and you want to import that particular model along with its mass and inertia properties, then you'll be using this first radio button. But you'll be using the second radio button, which is only to import the CAD or the FE model without bringing in its mass and inertia properties. It will be just importing the geometries from either a CAD file or from a FE file. So these are the two options that you have available in MotionView. Next, let's go to the input output file name section. So in the input file name drop down menu, here are the different file names file formats you can specify to import your particular model. So these are the extra file formats that have been added in the latest version. Okay, apart from the ones mentioned in the presentation. So you can select any of the particular file format, and this top folder that you can see, if you click on that, it has to direct you to the particular file that you want to import. So in this case, I've chosen the Parasolid file. So if there are any Parasolid files in the directory, then it will point to that particular Parasolid file. Once after selecting that, you can say open, and then this particular second folder that you can see is to save the file in the HTTP file format. You can give whatever name you want, and it will be saved as a .html file that can be accessed in MotionView. I hope it's clear. Next, the MDL options. So here, the first radio button is used to specify the system under which the geometry is imported, and you can give the necessary details for the body, point, graphic name, etc. So you can usually leave all these options as default under this section unless you have to specify something for a specific case. Okay, otherwise you can leave this particular section as default. So you can just minimize this and expand this based on your necessity. So now let's move on to the meshing options for the surface data. This is an important section in this particular dialog box. So if you select the first radio button, it will automatically mesh the geometry, but if you select this particular radio button and say OK, it will launch HyperMesh, and you can interactively create the mesh. So if you select the first option, it does an automatic meshing, but if you want to interactively mesh by launching HyperMesh, you can select the second option. So when you select this first radio button, which allows its automatic meshing, you can also check this particular option, which controls the mesh coarseness for the contacts. And this is a very useful option when you come to contact simulation, which will be covered in chapter 11. So you need to be very careful, because when you're dealing with 3D contact simulation, the two mesh geometries must have a relatively finer mesh when compared to the other simulations. So you can adjust the slider. So as from a scale of 1 to 10, if you go towards 10, you'll get a finer mesh, and if you're closer to 1, you get a coarser mesh. So the recommended value is to keep it somewhere between 5 and 6, okay, for the 3D contact simulation. Okay, so as a rule of thumb, you'd have to try maintaining, as I mentioned, 5 or 6 mesh coarseness. Now, if you select this particular option, wherein it opens HyperMesh for interactive meshing, then you need to be familiar with the HyperMesh environment, and also you need to have some basic idea about meshing to go ahead with this particular option. So it depends upon whether you're an MBD user, or you know some basics about FEA and HyperMesh. So you can select either of these two options. Okay, so coming to the last section in this utility, it is used to specify the coordinates or the node IDs of the FEM file for positioning the geometry or the graphic. You can go ahead, you can select which coordinates you want to position it in, and you can select the node IDs of the FE file, and you can give this particular information in this section. So, but usually you can leave it as default. So after selecting all these options, you need to hit OK. So now it's throwing an error message or a warning message saying that we don't have any files that are selected. But if you've selected all the options and if you click OK, it will go to the next part of the CAD import utility. It will pop up another dialog box which will list the bodies with the volume and mass information. So you can then change the unit type for the input file from the drop-down menu, and also select the bodies or a single body that you want to modify, either the density, etc. Okay, and finally when you hit OK, the CAD will be imported. Okay, so to become more familiar with this particular option, we have an exercise after this theory session, so I'll be showing that in the demo exercise. So let's go back to the presentation. So this is what we already covered. And we also covered this slide wherein I explained each of these options that are available in the CAD import utility dialog. And this was the second part of the dialog box that I was talking about, wherein after you select a particular file and hit OK, so this is what you're going to get. So in this, you can change the unit type in this option. You can also change, you can select a particular body and change its density. And please be aware that this can only be done during the time of the import of the file. You can't change its density later on during the model building process. So if you need to change any of the density values for any of these bodies that you're going to import, this is the time that you need to do it. while you're importing the particular model. So now let's move on to the next part of the presentation, which is regarding curves. So curves in motion view are mainly used as forces, motions, and constraints. So the non-linear characteristic of a force, such as spring force versus deformation, or damping force versus deformation velocity, etc., can be represented in the form of a 2D spline. Similarly, when the displacement versus time or the velocity versus time, etc., also can be represented in the form of a 2D curve. So we will now concentrate on how the curve can be used as a constraint we will concentrate on how the curve can be used as constraint in the next chapter when I explain regarding the curve to curve joint. So once you import the curve, it can be previewed in motion view as shown in this particular slide. So you have this option in motion view wherein you can specify a particular relationship between two entities using a curve. So you can have an Excel file having the X and Y values, and you can import that particular file, .csv file, into motion view. And before moving forward with your model building process, you can check if you've imported the right curve by previewing by clicking on the preview button that you have on this particular panel. You can preview the curve before moving forward. Okay, so I'll be showing that in the demo video that's there today. And one more important feature in motion view is that you also have the option of importing a 3D spline as well, not just a 2D spline. We can also import a 3D spline as well, okay, which is basically a graph that contains the data in the X, Y, and Z coordinates. So here you can say, you can give an example of a plot that has an RPM, engine RPM, versus the frequency versus the cylinder pressure of a particular engine. So you can take that as an example, and you can import that when you're trying to simulate a single cylinder working, single cylinder of an engine that's moving up and down, the piston moving up and down. So you can import a 3D spline which has the data in XYZ format for the RPM, frequency, and the cylinder pressure. So the curves panel, it allows you to add and edit curves, and the X and Y data vectors for a single curve can come from any of the sources such as file, a math, or values. So for example, the X data vector can come from a file, and the Y data vector can come as a mathematical function of X. So you have the flexibility in the import spline utility. Okay, so here this is what I was talking about. So when you have when you select the X option, the values where you have to input as the X values, then you can go to the drop down list and you'll have further options. Maybe I can show that in the graphical user interface so it's more clear. So let me go to import curve. So this option that you see on the screen, let me cancel this. So this option that you can see on the screen is to import a curve. Okay, so I'll say okay. The X values for that curve can either come from a file, as I mentioned, like a .csv file, an Excel file, or it can also be in the form of a mathematical expression, or you can just put X and Y values here. So what I'm trying to say is you can try to get the X values from either a file, math, or values format, and Y values need not necessarily be from the same source. So you can give this as, say, a file. You can import the X values from the file, and the Y values can be imported by giving a mathematical expression to create a function between the X and Y. So these are the flexibilities that you have while importing a curve in motion. So in this slide, I'm trying to cover the interpolation or the extrapolation functions using curves. So since the data in a curve is at a discrete point, okay, a function must be used to either interpolate or extrapolate the data for times when there is no direct data available at a point in the curve. So the interpolation can be done either by using Akima or the AKI SPL format, or the cubic, that is, it's specified as CUB SPL, or the quintic QUI SPL interpolation methods. So these are the three interpolation methods that are available in motion view. So these functions are supported in MotionSolve expression language. So now I'll try to explain each of these in detail. So both the Akima and cubic use cubic polynomials to perform interpolation. but differ in many ways that you need to know. You need to understand the difference when you'll have to use a Akima interpolation or when you'll have to use a cubic interpolation. Okay, so I'll get into that in a few seconds. So the Akima fitting algorithm, it uses local methods to calculate the spline coefficients. So here in this case, when you talk about the mathematics behind the Akima curve fitting, so no matrices are ever inverted. So for this reason, it is preferred when the reference spline that you have has many data points. So try to use the Akima interpolation method when the X and Y or the 2D spline or the 3D spline that you're creating has many data points. If it has very discrete data points, then try to refrain from using this particular method. So the main disadvantage of this method is that it has non-smooth derivatives, especially when the data points are not equally spaced. So the Akima method consequently must never be used for interpolating motion data. On the other hand, the cubic fitting algorithm, it ensures a much smoother fit by utilizing natural splines. Okay, it is much better at calculating derivatives of the resulting spline, but it has its own disadvantage. It is not good at modeling sharp corners in the data. Okay, for splines with two independent variables, such as the 3D splines, the interpolation along the second independent variable is always linear, regardless of the choice of interpolation along the first independent variable. So the interpolation or the extrapolation algorithm that you need to use is completely application dependent. So I have tried to use some of the the best algorithms that can use in a couple of cases, but you'll have to explore if you're building an own model, then you'll have to explore which particular interpolation method suits the best for your model. Okay, so it's totally application dependent. I'll be explaining about one of the functions that we'll be using in this particular chapter, in this particular exercise demo. That's the dx function. So this dx function, it computes the x component of the relative translational displacement of marker I with respect to marker j as resolved in the coordinate system of marker k. So the syntax for this particular dx function is dx, and the arguments will be I vector, j vector, I marker, j marker, and the k marker. Okay, so the I marker, it is the marker whose displacement is to be computed, whereas the j marker is the marker with respect to which the displacement is to be computed. So this argument is optional, okay, and it can be omitted if it defaults to the ground coordinate system. And the k marker is a resultant displacement vector, and it is resolved in the coordinate system of k marker. Okay, so this, if it is omitted, then again it defaults to the ground coordinate system. So this is the syntax for the dx function. I think it will become more clear when I try to explain this function when I'm using this in the exercise demo. Okay, now let's move on to the Hyperview collision detection algorithm. So in this chapter, we'll try to simulate the automotive trunk lid mechanism, as I mentioned earlier, using the 4-bar mechanism that we have built so far. So this is the first module that will be using all our basic knowledge that we have learned so far, and we'll try to stitch that together and use it in this particular exercise demo. When we simulate this model in Hyperview, it allows you to view and detect the collisions between the graphic objects of the current animation model during simulations. This is a very special capability that is present in Hyperview, and we'll be making use of this in our exercise demo. So in order to activate this option, you need to do the following. Just follow, I'm going to switch back to the graphical user interface to show that. So from motion view, I'll be switching back to Hyperview. So in order to have that option enabled, for me, it's already available on the screen because I've already enabled it, the collision detection icon. But if it is your first time, you won't be having this icon on your screen or on your toolbar. So in that case, you have to go to View and then go to Toolbars and then go to Hyperview, and you need to enable the Tools option. So you can see that if I disable this, that particular collision detection algorithm icon disappears from the toolbar. So you need to go to View, Toolbars, Hyperview, and select the Tools option to get collision detection algorithm icon on your toolbar. So now let me try to explain the different options available in this collision detection algorithm. So there are 4 important things that you need to know in this particular panel. The first thing is the collision sets. So the collision set is defined for a current model in this particular section. Okay, and then the next section of this panel is the selection. So you'll be selecting the components which you need to add to the group A and group B. And then it is the proximity section. So if you enable proximity, it will allow the objects to get detected at the distance that's specified as the minimum distance. Okay, and then you have the animation event section. So this is to control the animation that will be running on the screen. Okay, so let me explain each of this one by one. So a collision set is activated or deactivated using the radio button. Okay, so here you need to come, and if there is if you've imported a particular result file on your screen, so you can go ahead and select any of that and go and add it to group A. So you can go create because now it's not creating anything because we don't have any component on the screen or any results that are available on the screen. So you need to go, for example, for the automotive trunk link mechanism, the body in white structure of the car will be added to group A, and you can add the trunk to the group B. Okay, once you do that, you can enable proximity checking, this particular option. Okay, so it allows the objects to be detected at a distance specified as the minimum distance. So if you say, hey, detect the collision 1 unit before the collision or 1 mm before the collision, so it will do that. So you can vary this particular parameter. Okay, and then the next radio button is show the results by elements or components. So the difference in this, I think it is better when you visualize this. So I'll just try explaining this now. So when you select elements, it will try to show the elements that come into contact. So when 2 objects come into contact, the elements that are associated with those 2 geometric bodies will be highlighted as red if you select this option. But if you select the components option, then the elements that will be placed in that component, if the trunklet geometry, it belongs to the trunklet component, then the entire geometry will get highlighted. It's not just the elements that will be in contact, but it will be that entire component that will be highlighted in red. So that's the difference. I think it will become more clear if I show an animation on the screen. So I'll be doing that in the exercise demo. And next thing is the animation event. So here they have in the drop down menu, you have 2 options: to ignore collision and to stop on collision. So this means, so when you're trying to simulate the particular mechanism, and if there is a contact, so even if you've chosen ignore collision, it will still continue doing the same simulation even after the collision has happened. If you choose the second option, stop on collision, then it is going to stop when the collision occurs. Okay, so this is the basic idea of the collision detection algorithm. Okay, now let me go back to the presentation. Okay, so this is what I explained. So, and I think I put a picture on the screen. So this is what I was talking about. If you've selected elements, then only these elements, wherein this is the trunklet and this is the body in white structure of the car. So only at the locations, elements that come in contact with each other, you see it's being highlighted in red, like at this location and at this location. But if I had selected the components option, this entire trunklet would be red in color. Okay, the whole thing would be highlighted.